Hey guys, so I'm gonna go ahead and put up a warm-up exercise. Let's see. And yeah, I think we might have a bit of a lower turnout than normal today. So I might, let's see. We'll see how it goes. I think for now we can say, we'll pick back up at 5:12 or 5:13 or something as usual. Oh, whoops. But yeah, so let me just write up the exercise here. So find the closures of the following sets. So the first one here will be the set. The next one will be Q. So then the rational numbers. All the rational numbers for which r squared is less than 2. And actually, one extra one, the set S, which is the set of n over 2 to the k, such that n and k are in Z, and n and k are greater than or equal to 0. Yeah, let's say that. So that'll be the warm-up. Let's actually resume at 5, let's say 5:15.
Can we assume that they're part of the metric space like R?
Yeah. In R. Very good question, actually. Yeah, I meant to say that, and yeah, but yeah, so good. Hey, all right. So let's kind of go over this real quick, and then I'll be happy to take questions and stuff after that. And then, of course, I have some more exercises picked out. No surprises this time, hopefully. Although I will say on that note, in case you guys didn't see it in the announcement, one of the announcements I posted yesterday, I mentioned that. So I made a video explaining, for those of you who were here yesterday, I think you were all here, but yeah, so we did that one problem that was like showing the lim sup of the product sequence is like less than or equal to the product of the lim sups. There's actually like a way better solution to that problem than what I did in the actual discussion. And it doesn't use any like annoying epsilons or anything. It's really cool. So yeah, I definitely recommend you check that out if you get a chance. Because the technique in there is actually like good. I mean, it's like it's a powerful thing if you can sort of get used to it. Anyway, yeah, let's go over this real quick. So what's the closure of this set? Anyone?
Is 1 over n union 0?
Yep. Yeah, so the only point in the closure that isn't already in the set is just the point 0. Because if you sort of imagine forming any sequence of these points, I mean, really that sequence will have to converge to 0. Well, okay, and actually, well, if you're allowed to repeat points, that's not necessarily true. But either it converges to 0 or it just like converges to one of the numbers already in the set if you like repeat that number infinitely many times, right? So yeah, so this is 1 over n over n in n union 0. Very good. What about this one? The closure.
Is it the set of irrational numbers?
Not quite, because you wouldn't want to exclude the rational numbers.
The real number line? Is it?
Yeah, exactly. Okay. Yeah. It's everything. Yeah. So actually, as a rule, any set is always a subset of its own closure. And I mean, the reason for that really is just that you can imagine, like, if you want to think about it in terms of like sequences, right? And like limits of sequences and stuff, like you can always form a sequence that's just like repeating the same point from E over and over again. So like every point in E has to be in the closure. But also like from the definition, the closure is the intersection of all the closed sets that contain the set E. So because E is automatically contained in all of those sets, it has to be in the intersection of all of them. But yeah, so yeah, this is R, and the reason is precisely that every real number has an approximating sequence of rational numbers, right? Like an easy way to do it would just be like a similar thing to what I did before, right? Remember when we looked at like a set kind of like this one, and we tried to form a sequence approaching 1/3, and I just kind of like took these like maximal like approximating terms for like different values of k down here. You can do something really similar for this and say like if you're given like a random real number, consider all the multiples of like all the integers, like find the floor of the real number, and then all the multiples of 1/2 and like find the biggest one of those that's less than your number, and then all the multiples of 1/3 and all the multiples of 1/4 and so on, and just keep like refining your approximation that way. And you'll get a sequence of rational numbers approaching any real number you want. So how about the closure of this one? So it's kind of it's similar, right? Because it is it's like a chunk of the rational numbers, right? It's just that this is all the rational numbers that lie between negative square root of 2 and square root of 2, right? So we should expect the closure of this to be negative square root of 2, square root of 2, right? Because by the same kind of principle up here, you know, any of the real numbers between these things, you can make a bunch of, you can make a sequence of rational numbers approach that. Actually, an even easier way to argue that there's a sequence of rational numbers approaching any real number is just use the denseness, right? We already know the denseness of Q tells us that like there exists a rational number in any interval, you know, a, b, right? So what you can do is take a given real number and then like take some interval around it, like, you know, do like x minus 1, x plus 1. Okay, there exists a rational number in that interval. Okay, x minus 1/2, x plus 1/2, there exists a rational number in that interval, right? X minus a third, x plus a third, and so on. And just keep picking rational numbers that way, and you'll get a sequence. And you can do that for like any of these sets. You can do it for this set too, right? And in fact, actually, it's funny. So the term denseness, another aside here, in general, a subset E of like, well, how to describe this? I don't know. Like F is like dense if like E closure, oops, equals F. Roughly speaking, this is actually not quite how the term is normally used. Normally we would say like a subset is dense in a metric space if the closure is like the entire metric space. But so this would be like dense in F, I guess. It's sort of, I don't know, whatever, it doesn't matter. But yeah, so the term denseness here is actually related to is like, it doesn't have so much to do with the fact that there's a rational number between any two real numbers. And it has a lot more to do with the fact that like the topology on the real numbers is such that the closure of the rational numbers is the entire real line. That's the real meaning of the term denseness here. It just turns out that these two things are equivalent to each other. Okay, so the very last thing here, what do you guys think this is? So. Any guesses?
Is it Q? No.
Not quite.
Okay.
So if we think about the numbers in here, right? You can get like, so if k is like 0, right? Then you can get all the integers, or all the non-negative integers that way. So you can get like 0 and 1 and 2 and 3 and so on, right? If k is 1, then you get all the multiples of a half, right? And if k is 2, you get all the multiples of a quarter and so on. So at least the closure of this set is probably restricted to like the positive half of the number line, just because all of the numbers in here are like non-negative. Sorry, the non-negative half, right? But then the other thing is like, okay, if you think about like how these numbers are distributed on the real number line, as k gets really large, right, they get packed closer and closer and closer together, right? So it's kind of the same phenomenon as q, right? If you think about q is like dense in the sense that like no matter how small of an interval you look at, there's still a bunch of rational numbers in there. The same thing is true for this set, right? Like if you pick a really tiny interval on the number line, just by making k super big, you'll still find a bunch of these numbers like inside of that interval, right? So actually pretty much by the exact same logic as up here, the closure of S has to be like 0 infinity, right? Because any real number, I mean, you can do the exact same thing, basically. You can play the same game. If you take any real number between 0 and infinity, then by just shrinking, you can just take like smaller and smaller intervals around it, and you can always still find a number from this set that's inside of that interval. So you can build a sequence that way, right? You can build a sequence that converges to any real number you want in this set, basically. Okay, so that's kind of like, that's the way you want to think about like closed sets or like closures of sets in the real line. If you're just trying to sort of compute in your head, like if you have some set you're looking at and you're like, okay, what's the closure of this? Like a good thing to think about is just like, okay, where are the like what numbers are these like clustered around, or like where are the numbers in the given set like dense with each other, or like, you know, or what limits can you achieve by taking sequences of points in the set, right? Those are all kind of related questions that'll help you figure out what the closure should be. Okay. Are there any questions about this exercise overall, about closures? Okay. How about in general? Oh, just general questions. I'll open it up. Anyone have any questions?
I actually have a question,
Mm-hmm.
but it's like not about lecture 8. It's just like a very general question. So like you mentioned that if we want to prove alpha is smaller or equal than L, first of all, we just like let alpha smaller or equal than L1 for all L1 is greater than L, right? And this way.
Well, it's more like, okay, if we want to show out some alpha is less than or equal to L,
yeah,
then we can prove that alpha is less than or equal to L1 for all
L1 is greater
L1 greater than L. Yeah, you can do that. Yeah.
But like I try to draw it by myself, but you said that like if alpha is smaller or equal than L, if alpha is bigger than L, then L1 must exist in between L and alpha.
Yeah.
But like, is it possible that alpha exists between L and L1?
Well, no, because the thing is, right, like the point is that if we show that this is true for all L1 greater than L, then the point is that like we can pick any L1 we want and we'll know that alpha has to be less than or equal to that, right?
Yeah.
So the point is like it would be a contradiction if we like, okay, let me draw. So here's L, right?
Yeah.
So let's imagine, so, and when I say then, what I really mean is to show this, right? We can prove this instead. So what I'm claiming is that if this is true, so let's call this like 2, and let's call this 1, all right? So if 2 holds, then 1 holds. Okay, that's what I'm saying. And so let's imagine what would happen. So y. Suppose 2 holds, but 1 does not, right? Yeah. So then what that means is, okay, so if this holds, so then, but so let's, if 1 does not hold, right? If this does not hold, that means alpha is bigger than L, okay? So let's put alpha over here, right? But then if 2 also holds, we should be able to pick any value of L1 bigger than L, and it would, and know that alpha is less than or equal to L1, right?
Yeah.
So sure, we could pick L1 over here, and then there would be no problem, right? There would be no contradiction. But the problem is we're allowed to pick any value of L1 bigger than L, right?
Yeah.
But we can also just as well pick L1 over here, right? But if we pick L1 over here, then alpha is not less than or equal to L1, right?
Yeah.
So 2 is actually false, right? Alpha is not less than or equal to L1 for all L1 bigger than L.
Oh,
because
okay.
we found an L1 where that's false, right?
Yes. Okay.
So this is really, it's the for all thing here that makes this imply this one.
Mm,
Yeah.
okay. Got it.
Mm-hmm.
Thank you.
Any other questions?
Yeah, I had a question. Sorry.
Mhm.
Also kind of general. So is there a more like, I don't know, how do I say, like formal way of finding lim sup and lim if other than just like looking at the sequence and kind of like seeing where it converges to, or like, uh,
Yeah, I mean, if you really want to like prove something is like the lim sup or the lim inf, right? Like at this point, I would say that the best tool you have at your disposal is to think about like find a way to argue what the set of subsequential limits is basically, and then just say like, okay, the lim sup is the supremum of the set of subsequential limits. So like what you could do is say like, okay, for one thing, so let's say we want to rigorously prove that lim sup Sn is a certain number or something, right? We can, let, oops. Well, I mean, I don't know, actually, there's sort of two different ways of doing this. Like one thing you could do is just like, one approach would be to calculate with proof the sequence V capital N, which is the supremum of Sn for n greater than capital N, right? So you could actually try to find, some way of describing this sequence and then show, the limit of Vn is the, desired number. But usually there's some ways, usually like there are ways to kind of like, cut corners here or something. Another approach would be to like let, SNK be a subsequence, a convergent subsequence. Show the limit of SNK as k goes to infinity is like less than or equal to the desired number, right? And then also, also show there exists a subsequence converging to the desired number, right? So this one would establish that the number in question, if you think you know what the lim sup is, this one would establish that the lim sup is less than or equal to the desired number, and this one would establish that it's greater than or equal to the desired number.
okay, I think that, yeah, that makes sense.
Uh-huh. Any other questions? All right. Let's see. So I just have a couple. These should be like, hopefully, I know the definitions are still kind of fresh and stuff. So like, when I say that these exercises are straightforward, I don't mean that they should be like easy or immediate. I just mean that like, you don't have to do anything tricky with the definitions. You just have to like understand the definitions and the theorems, I guess. So let's do this one. Yeah. Let E be a subset of RK. Show E is compact if and only if every sequence in E has a limit in E. Oops. Okay. So, and this should be, I kind of wanted, I think, well, okay, we'll see. We'll see. Yeah, I think I'm gonna, so since there's only like 4 of you guys, I'm gonna just put you all in one group here. But I'll give you a little room where you can, talk to each other. That won't be, recorded on the on the final like video and stuff. So let's see. Let me make this. There we go. And yeah, let's resume at like 5:45 or something, or maybe 5:48. Oh man, all right. Yeah, sorry guys. I kind of messed. I hope you, I don't know. Did you guys like figure out what it was supposed to be saying? I mean, not that I expected you to, but you know, yeah. It's kind of ridiculous to say that like every sequence should have a limit in, you know, obviously. But yeah, I guess what you could say is, well, yeah. Yeah, sorry. I kind of messed that up. But the idea was to use the Heine-Borel theorem basically to go both ways. I don't know. How far did you guys get?
I mean, the forward direction. Oh,
Yeah, go ahead.
the forward direction was pretty easy to do because like you use a Heine-Borel, and then by definition of closed, then you can use the sequence. But then the other way I had to prove that it's bounded.
Right. Yeah. Okay.
And proving it's bounded is kind of hard.
Yeah, that is a little bit trickier. Any other comments? Yeah. Okay. So I'll sort of go through this now. And again, I'm sorry for like every once in a while I just make these weird typos. Yeah, I'll be more careful. But yeah. Anyway, so yeah, let's. So if you go forward, right, that's pretty straightforward. So by Heine-Borel, E is closed and bounded. It's actually like a little bit more nuanced because so let Sn be a sequence in E. So then like, first of all, you have to get a convergent subsequence in the first place, right? And that comes from the Bolzano-Weierstrass theorem. So because the original sequence Sn might not converge at all, right? So then since E is closed, that's how you know Snk approaches a point in E as k goes to infinity, right? So any questions about that? Okay. So let's look at the other direction. So this one is like, so to prove boundedness, you actually basically want to do it like by contradiction kind of. So what you can do is you can show that if it's not bounded, okay, hold on. So this direction, suppose every sequence, I mean, you don't even actually have to make this supposition. So what you can do is say, so you can do it by like contrapositive. So suppose E is not bounded for one thing, right? Then there exists, so then yeah. So for each, what you can do is like for each n in n, there exists a, point, say xn in E with like the distance from xn to 0 being like greater than n, right? Does that make sense?
Wait, can you explain a little bit about that?
So basically, if E is not bounded, right, what that means is that like you have to be able to find points that are like arbitrarily far away from 0.
Yeah.
Because if you couldn't, right, if you couldn't find points that are arbitrarily far away from 0, then there would be some like upper bound on how big the distance from 0 could get, right?
Oh, yes.
And if there was an upper bound on that, then you could find some big, sphere around 0 that contains all the points in E, and that would mean E was bounded, right?
Oh, okay.
Yeah. So if E is not bounded, you have to be able to find a point with however big of a radius you want, basically, or at least one point has to have a radius bigger than like any particular number you pick, right?
Yes.
So what I'm doing is I'm basically picking a sequence of points where like the radius gets bigger and bigger and bigger and approaches infinity. Or what by radius I mean like distance from 0, right?
Yeah.
Or length, I guess, if you want to call it that, the length of xn. So basically, these kind of like go out, you know, to infinity or whatever, and then any subsequence. So then any subsequence of the sequence xn fails to converge, basically, right? Because the distance of xn k, let's say, to 0 goes to infinity, right?
Yeah.
And if you're really like, if you want to be super careful about this, you can say like the distance from xn k to like any point, call it a or whatever, goes to infinity because you can do like a triangle inequality to show that if the distance from xnk to 0 goes to infinity, then the distance from xnk to any fixed point, if you fix your attention on any point anywhere, then this distance eventually goes to infinity.
Just curious, but does that make xn infinite subcover in this case? Like would be like
kind of.
Okay.
Yeah. What you can do is like, okay, for unbounded sets, you can form open covers by taking, like you can sort of take, actually like one open cover of E would be like just if you formed these like open balls. So basically if you set un equals like the set of x in E with the distance from x to 0 less than n, right? Strictly less than n, okay?
Yeah.
Then un is the ball of radius n around the origin, right?
Mhm.
And it's open. So each un is an open set. So then the set of all un is an open cover. Oh God. Okay. Whatever. So the set of all un is an open cover because I mean the union of all these un is actually like the entirety of RK, right?
Yeah.
So clearly they cover E. And then actually, this is actually this is like a more elegant argument. So thanks for bringing this up. Any finite subcover, right? Any finite or not finite subcover, but any finite subset of these open sets, right? There's going to be like a biggest one, right? So if you just look at the biggest one out of all the finitely many un, there's going to have to be points in E that are outside of that, right? Because E is unbounded. So there's no finite subcover of this open cover of E. So that actually just directly proves that E is not compact if E is not bounded. Does that make sense?
Yes, now it makes so much sense.
Yeah. So so actually what we wanted to do, but we were trying to show that that this condition gets violated. So actually this doesn't quite do it, but spiritually it's like the same thing happening basically in each of these. So actually, we do still have to kind of do this because what we're trying to show is that there exists a sequence with no subsequence having a limit inside of E. Yeah, sorry. So this is kind of an aside, but we do still have to make this argument. Anyway, so there's some triangle inequality thing you can do here. I can't, I don't know. I don't want to get bogged down in it right now. But so this is what happens if E is not bounded. But we also still have to say, like, if E is not closed, then there's a different argument to make. But that's just like by 13.9, I think you can say. So let me just go through this quickly. So suppose E is not closed, right? Then I think, I'm pretty sure, right? 13.9, yeah. By 13.9b, there exists a sequence Sn, well, I don't know, Xn, convergent sequence in E whose limit, is not in E. Okay. Then any subsequence of Xn converges to the same limit, right, which is not in E. So again, we end up violating the second condition, right? Like, the whole thing that I'm trying to do here is just say, like, okay, if you violate the assumption that E is compact, then you end up violating the second condition here, right? If we call this 1 and we call this 2, what we ended up showing is that I'm actually gonna erase this. What we ended up showing was, like, if either 1 or 2, or sorry, if either closedness or boundedness fails, then 2 fails, right? That's what I just showed. Because so what I said is, like, okay, if E is not bounded, then 2 fails, right? And if E is not closed, then 2 fails, right? This thing about sequences, right? So if either of those two things fails, or if either closedness or boundedness fails, then 2 fails. What that means is that if 2 is true, then the original set has to be both closed and bounded, right? So that means that it has to be compact, or sorry, yeah, or yeah, that's what we wanted to do. Yeah, that's what we were trying to do. We're trying to show 2 implies 1. So what I showed is that if 1 is false, then 2 is false. That's the contrapositive.
Hi, Professor. I wonder, besides contrapositive, is there any other way for us to prove things?
Let's see. Yeah. I guess what you could say is, suppose there's subsequence of the limit E. Actually, off the top of my head, I can't really think of a different way of approaching this.
Yeah, but like usually this is a very useful way, right? So if we can't think of a direct way to prove backward, we can just like use contrapositive. If not A, then not B, and then.
Yeah. So yeah, we showed, like, the forward direction directly, and then we showed the backward direction by contrapositive. Yeah, that's perfectly fine.
Okay.
Yeah, so it's just like, we basically said, like, okay, assume E is compact, then every sequence blah blah blah.
Yeah.
Assume E is not compact, then this thing is not true, right? Yep. Yeah, so okay, yeah, it's a little bit of a complicated argument, but I hope the, like, main ideas are clear. Okay, so there are, like, 2 main ideas before we adjourn. Okay, I know it's, like, kind of time to go now. There are two main ideas that I want you to take away from this, right? The first one is that the boundedness condition makes sure that you can't like make sequences that fail to have limits in E just by like running off to infinity, right? And then the closedness condition means that you can't make sequences that fail to have a limit in E just by kind of like approaching some point that happens not to be in E, basically, right? There's sort of like, there are two ways that a sequence can try to like escape from the set, right?
Yeah.
And one of them is by going to infinity, and one of them is by approaching some kind of like boundary point that happens not to be in the set that you're looking at, basically. Okay. And so it's like compactness is basically this like condition that makes sure that neither of those things can happen. Okay.
Yes.
Yeah. So anyway, thank you guys for coming and sticking with the material, because I know that, you know, this is like some of the most challenging material in the class right now. It will get a little bit easier after this. But so I think, you know, with this kind of stuff, it's just like patience is totally key, and just like doing more and more problems. And like, even when you do a problem, like keep thinking about it, think about the solution, look back at the definitions, and just like keep throwing yourself into it, I guess. And it'll eventually start to make sense. Okay. So yeah, perseverance is key. And it's good that you guys are, you know, coming and trying to stay on top of the lectures and stuff. And I appreciate it. So anyway.
Thank you so much, Professor.
Yep.
A quick question.
Yeah.
Is this the scope of, is this all what the scope of what's going to be on the coming midterm?
Yep. This is
None
it.
of the
Yep.
lecture on Monday? Okay.
No. There will, so Monday is going to be, there's going to be a review session. There won't even be like a
okay.
lecture. I mean, maybe I'll post the lecture, but it's technically going to be the lecture that's scheduled for like Wednesday. So
Okay, cool.
there's not formally a lecture scheduled for Monday. I'm going to have like probably maybe a 2 or 3 hour live review session that I'll make an announcement about.
Okay,
and
cool.
it'll just be like, I'll have some exercises picked out maybe, but it'll be mainly intended for people to like ask questions and stuff. So it's kind of like office hours. But yeah.
Okay.
All right. So, yep. See you guys.
Thank you so much. Bye.
Bye-bye.
Thanks.